Hello class, these are notes 13.1. We're going to move into a topic called series, and we'll start out by looking at what those series are. In order to understand series, we need to understand what a sequence is, and a sequence is any ordered list. Any type of list that we want. Here's the notation that we use. We use these little curly brackets to determine what that list is, and then n for the nth term in this, or a to the nth, or the nth a will be our nth term depending on how many are in that list. So let's take a look at these and do a quick little review from our algebra days. And you'll see that we have a list of items here that we can put in the fancy brackets to say this is a sequence. And you'll notice that each time we're subtracting 3 to get to our next term. So that means the next term will be -4. Subtract 3 from that, and that will give us -7. The first term is, in this sequence, 8. And we use t sub 1 or a sub 1 if we wanted to do that, but I use a t here for term 1. And then you'll see that there's a common difference between these, and that common difference is -3. Therefore, we can write an explicit formula by saying the nth term is always going to be that common difference, -3, times n minus 1. That means if I want the 9th term, I would take 9 minus 1, multiply it by -3, and that will give me, oops, I forgot my first term in here, didn't I? So that would not work. I also need to add that first term to this. Okay? So you can see in our explicit formula that our explicit formula includes the first term and that common difference. Let's try another one. You'll see in this one that if I try subtracting, I can subtract 4, but subtracting 4 won't give me 2. So subtraction's not going to be used in this one, but I do notice that in this one, if I multiply by 1/2, multiply by 1/2, multiply by 1/2 each time, I will get the next term. And of course, 1 times 1/2 is 1/2, times another 1/2 would give us 1/4. So in this one, we do have a first term that is 8, that matched what we had before, but this time there's not a common difference between these two, there's a common ratio between these two. And that is, the next one's half as big as the previous one. Therefore, we can write our explicit formula for this one. It's going to be 8 times our common ratio to the n minus 1 power. So let's summarize both of these again. You can see both of these include our first term. One of them has a common difference. This one has a common ratio, which means these two sequences are our two main types. You can see that our first one is the arithmetic. Arithmetic, when we write the explicit formula for this, it will always be t sub n equals our first term plus the common difference between all of them times n minus 1. It has to be the same difference between all of those. In this case, it's a -3. Okay. Then, if we can't get to the next term through addition or subtraction, but we get that way through multiplication, then it is a geometric sequence. in the geometric sequence, we can write the explicit formula by saying t sub n equals our first term, t sub 1, times the common ratio raised to the n minus 1 power. So we have some sequences that can be an infinite one. And since they're infinite, we need to reevaluate or address our issues of convergence that we've talked about in previous sessions. So let's talk about this. Let a sub n be the value of the nth term of a sequence. If n is a real number, then the sequence is finite. 7 terms, 8 terms, 28 terms, okay, even 100 terms. If that's n, then we know it's finite. But if n goes to infinity, then the sequence will have is what we would call an infinite sequence because it has infinite terms. So when we consider infinite sequences, let's look at these two limits. So if I evaluate the limit of this and the nth term as I go to infinity equals some number, then the terms will, then each one of the terms will converge. So in other words, if I go to infinity and it looks like I'm equaling some value, then I know it's going to converge to that. But if it doesn't equal some number, okay, then our sequence will diverge. It doesn't go to some number, then we will diverge. Let's consider this sequence here. This sequence is called the harmonic sequence. It's a very special case. Okay. And you can see in this one that each term, the nth term in this is always 1 over n. So you'll see the fourth term is 1 over 4. Second term is 1 over 2. First term is 1 over 1. Now, will this converge or not? Well, let's go ahead and evaluate the limit as n goes to infinity of this. So will the terms go to a common number or will they not go to a common number? Well, you can see with this, as n goes to infinity, we got an awful big number in the denominator, which of course we should recognize from our dealings with limits that this is obviously going to go to 0. So yes, it does converge. And what does it converge to? It's going to go to 0. Our nth term will be 0. And all of those terms are going to get closer and closer to 0. And you can just see from this, I'm dividing 1 by 4, and then by 5, then by 6. I'm getting smaller and smaller and smaller. Now, this same series can be also looked at and considered when it is an alternating series. And when we say this harmonic series is alternating, what we mean is our first term is 1 and the second term is 1/2, but we're going to alternate between positive and negative. So we'll have a positive 1/5 and then a negative 1/6. And that pattern will continue on and on, so that we know that we'll have one term over here, say a to the n minus 1. We'll just say that's a positive value. And then the next one, a sub n, would be negative. And then if there were more, we could say we'll have a positive 1 over n plus 1. And then the next one would be negative 1 over n plus 2, and so on. So you can see each term is going to alternate between them. And we can also write an expression for every single one of those terms, and this is an a, not a 9. A sub n would equal negative 1 to the n plus 1 divided by 1. So you can see our first term, this would be 1 plus 1 or 2, so the negative 1 would be squared, and we'd get positive over 1. Our second term, we'd say 2 plus 1, which is 3. Negative 1 cubed is a negative 1, and of course this would be over 2. So you can see where this is going to allow us to go positive, negative, and positive, negative. So let's take a look at some of these. You can see the notation given in each one of these is saying that we've got these terms, A or B or T. That nomenclature there is insignificant which letter I use, but this saying that each term in this sequence can be found by substituting in the number of the term for n. So for example here, a sub 1 would be 1 over 1 plus 1. A sub 2 would be, put in 2 here, this would be 2 over 2 plus 1, or 3. And then our third term would be 3 over 4. Our fourth term would be 4 over 5. Now, let's answer this question here. Will this converge to a single value, or will it keep changing and not go to a single value? So let's go ahead and evaluate this. Limit as n goes to infinity of n over n plus 1. We've seen this many times before. We can actually kind of reconsider this to say, if you wanted to, well, this is basically just n divided by n, because when I get really, really, really big, adding 1 isn't going to matter to us. So this is going to go down, or go to 1. And you can probably even see from this pattern here, we'd have 5/6, 9/10, 20 over 21, 100 over 101, and you can see that these numbers are going to slowly get and approach 1. So yes, this one does converge, and it does converge to 1. Let's take a look at our next one. This one, our very first term, b sub 1, this would have to be a negative 1 on top, and on bottom a positive 1, so we just get 1. If we look at our second term, we're going to square that, so we get a positive 1 over 2. Our third term will be back to a negative, and of course we'll put this over 3. And then our fourth term will be back to positive, and this will be 4. So let's evaluate this one. The limit as n goes to infinity of negative 1 to the n over n. And what's this going to be? Well, you can see we're going positive, negative up here. So it's either going to be a positive 1 or a negative 1. But of course the denominator is going to be a really, really huge number. So we'll keep bouncing back and forth, positive, negative, but we're going to keep bouncing back and forth on each side of 0 until we finally get so close to 0 that this is 0. So does this converge? Well, yes. B sub n does converge. Let's take a look at our next one. In this one, our first term, I better put a 1 there, would be negative 1 to the first power, which would be negative 1. Our second term would be negative 1 squared, which is a positive 1. Our third term, negative 1 to the negative third power, would be negative. Our fourth term would be back to positive. So if we evaluate the limit as n goes to infinity of negative 1 to the n, you'll see that all my answers are either positive 1 or negative 1. But when I look the definition of does it converge, it has to converge to a single number. We're not converging to a single number, we're actually converging to two different numbers. And it's not like the last one where I keep getting closer and closer to 0. This, I'm either 1 away from 0 on the right or 1 away from 0 on the left. Therefore, T sub n diverges. Okay? Let's take a look at our next one. In this one, T sub 1 times 3 divided by 2 to the first power. Next one would be 2 times 3, 6. And then, of course, that would be 2 squared, which would be 4. That does simplify to 3 halves. Let's take a look at our next one. T sub 3 would be 3 times 3, which is 9. And then 2 to the third power gives us 8. Then we get T sub 4 would be 3 times 4, which of course is 12. And then our denominator would be 2 to the fourth power, which is 16. That does simplify to 3/4. So let's evaluate this and see. Limit as n goes to infinity of 3n over 2 to the n. Well, since this is looking like an infinity divided by infinity, we have to do the AP rule, and that's say the limit as n goes to infinity of 3 times n is infinity, and the limit as n goes to infinity of 2 to the n is infinity. Therefore, we can use our L'Hopital, which means we're going to take the derivative of the numerator, limit as n goes to infinity, which would be 3, and then take the derivative of the denominator. And our denominator will be the natural log of 2 times 2 to the n. And you'll see with this that we're actually going to go to 0, because 3, of course, is 3 at infinity, but 2 to infinity is going to be a really huge number. Therefore, this is 0. And believe it or not, even though this didn't look like much here, and was kind of hard to see if there was any pattern in the first 4, this one actually is going to converge, since the limit as n goes to infinity goes to some number. So that's how we evaluate and consider sequences. Now let's talk about series. A series is a sum of the terms in a sequence. So if I have a sequence and then add up all the terms in the sequence, then I have what's called a series. And here is the notation. This symbol here is kind of a Greek symbol to represent the sum. We're going to add everything up on that. Okay? So if k is a real number, as we go from n to k, if k is a real number, then technically we don't have a series, we have a finite series. So let's evaluate each one of these. You'll see in the first one, we're going from n equals 5 to 8. So first of all, we'll put in 5 in here. 10 minus 1 would give us 9. Then we'd have 12 minus 1, which would be 11. And then 7 times 2, 14 minus 1 would be 13. And then we do the 8. 16 minus 1 would give us 15. Add all these up, and this sum is 48. On our next one, we're going from n equals 0. So let's add these up. When n is 0, this will be a 1. 1 times 4 is 4. Plus n equals 1 will give us 2/3 times 4, which will be 8/3. Then when we get to our last term in this series, the n is 2. We will square both of those, and that'll give us 4/9 times 4 will be 16/9. If we get a bunch of common denominators together, add these up, we get 76/9. Okay? If n goes to infinity, then the series is infinite. Okay? In calculus, really all we do is consider the infinite series. We really don't need any special math to do the finite series. So in calculus, when we hear the word series, unless it specifically says, hey, we're only looking at this many terms in it, the term series is implying that it is infinite. Okay? So let's take a look at one. This one right here, our good old heart. We've got 1/2, and then if we add 1/4 to that, and then we add 1/8 to it, and then we add 1/16, and then we add, you can probably see what's happening here. I'm doubling my denominator. I'm multiplying or taking half of each one of those. Let's see what this would go to. And the reason you see this little square over here is I can help you figure out what this series sum is going to be by taking this square and saying, let's take half of this square and then add 1/4 of this square and then add 1/8 of this square, and then let's add a 16th of the square, and then can you see where I can add a 32nd, a 64th to it, then 1/28 of it, and I just keep going and adding and adding, and hopefully you can see each time I add that next term that I'm closing this in, getting closer and closer to a point where when I go to infinity, I can no longer see any gap in here, and the sum is 1. That is of an infinite series. Now, I mentioned that series are implied to be infinite, but we can look at only some of the terms in that series, and that's when we use the term partial sum. So if I've got this series, n with infinite number of terms, starting with the first term and going to infinity, this of course would be, or can be written as a sub 1 plus a sub 2 plus a sub 3 plus a sub n plus, and of course I'm going to infinity. If I have something that looks like this notation is used to say I'm only dealing with a partial sum of this, not an infinite sum, not a series. I'm talking about a partial sum. So we have this one, and if I say I want to get the partial sum of this, here's what I'll do. Okay, and you can see it's asking me to do the first 4 partial sums. So the first partial sum would just be the sum of the very first term. So I put in 1, 2 to the first power is 2, and I have 1. If I want the second partial sum, I'm going to take that first term and then add the second term. That, of course, would be 2 squared in the denominator, or 1/4. Add that together, and I would get 3/4. My second partial sum is 3/4. The third partial sum would take those first 3 terms, 1/2 plus 1/4 that we have already, and then, of course, when I put in 3, this will be plus 1/8, which will give me a sum of 7/8. And let's take a look at our fourth partial sum. I should be more specific. This fourth partial sum will have the 1/2 plus the 1/4 plus the 1/8. And then my next term will be 2 to the 4th power, or 16, for a total of 15/16. And hopefully you can see that this first three terms are the third partial sum. So one way of getting the fourth partial sum would be to take the third partial sum and then just add that fourth term to it. So I could take that 7/8 that I calculated up here and then just add that fourth, or the next term here, the 1/16, and I'll get 15/16 this way too. No preference. Obviously, if you've calculated, no reason to add those up and do them again. So if, as n goes to infinity, we get a partial sum of some number, L, where L is a number, then the infinite series has a sum, or we use the word converges. So we can write it like this: the limit as n goes to infinity of our infinite sum equals some value. If it doesn't equal some number, then this will diverge. Yeah? Let's talk about these a little bit more in detail. So if we have a geometric series, their sum is relatively easy to get. But if we don't have one of those, then finding this infinite sum, this series value, can be difficult and even impossible. So the emphasis here is going to be on estimation. What are we approaching? The first step in this process is determine whether the series converges by using certain tests. Today we're only going to look at two of those tests. The first one is our Nth Term Test. Okay. So the nth term of a series must approach 0, or the series will converge. Okay? Remember, I'm adding a bunch of numbers together in this. Okay? And this one that's way out here has to approach 0, because if it's anything but 0, I'm adding something to that sum. If this goes to 0, then it's saying, if it's getting closer and closer to 0, it's saying, well, you know what? I'm really adding nothing to this. Right? So the nth term must approach 0 for this to diverge. Okay? If the nth term does not equal 0, then this will diverge. Okay? If it does approach 0, here's a caveat we have to be careful of, then the series might converge. If we get 0 here, we actually need to check and use some other method to make sure that it converges. So sometimes this nth term test, you'll see some professors will call this the divergence test, because the only thing that it verifies is that the series diverges. It will say, yes, it diverges, otherwise we're not sure. Okay. So let's use this here. And so first of all, it says let's write the first three terms in the general terms. The general term. This is a good practice that you'll need to get into. Let's watch this. You'll see that my very first term will be 3 over 10. This second term will have 10 squared, or 100. as the denominator. We're still going to maintain 3 in the numerator for every one of these. And then, of course, 10 to the third power would be 1,000. So those are the first 3 terms. And then I'm going to put a dot, dot, dot to indicate that now I'm going to put my general term, and that is just going to be 3 over 10 to the n, and then make sure that you continue with a plus dot, dot, dot to indicate that this is going on forever and ever. Now it says let's use the nth term test to decide if this diverges. Well, the first thing we need to do is check our nth term. Limit as n goes to infinity of 3 over 10 to the n. As this gets bigger and bigger and bigger, you'll see that this goes to 0. Okay? Therefore, since it goes to 0, we can't say for sure whether it converges, okay? But we can say it might converge. As a matter of fact, we could even say it might diverge. Either way, we've got to use another test, which right now we don't know. Let's take a look at our next one. In this one, we'll have 1 times sine of 1 plus 2 times the sine of 1/2 plus 3 times the sine of 1/3 plus dot, 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 n times sine of 1/n plus dot, dot, dot. So those are the first 3 terms and our general term. Now let's evaluate this. The limit as n goes to infinity of n times the sine of 1 over n. In this case, you'll see that we get infinity times 0. This is indeterminate. Okay? This is not 0. You can't say 0 times anything is 0. It might be 0, it might not be. We don't know the relationship between these two. Okay? So, since this can't be determined, we need to rewrite this thing. Okay? Because if I rewrite this as sine of 1 over n over 1 over n, then I can say the limit as n goes to infinity of the sine of 1 over n equals 0, and the limit as n goes to infinity of 1 over n is 0, I can use L'Hopital. Okay, run out of room there, but I'm just going to squeeze this guy in down here. So the limit as n goes to infinity, I'll take the derivative of this, and derivative of the outside, cosine, keep the inside, 1 over n, times the derivative of the inside. The derivative of the inside will be a negative n to the negative second power. That's my numerator. Now the denominator is going to be the derivative of 1 over n, which will be negative n to the negative second power. Just using my power rule, exponent minus 1. So you'll see that this actually worked out well for us because these two guys become 1. They cancel each other out, and this simplifies to the limit as n goes to infinity of the cosine of 1 over n. Well, this is just going to be the cosine of 0, which is 1. So another proof to you guys that this does not equal 0. Infinity times 0 in this case actually equals 1. And since that equals 1, then 1 is not 0, this diverges. Because as we go to infinity, we just keep adding 1 each time, and then 1, and then 1, and the next term is 1. So we never end up stopping at some value for our sum, because the next term is just going to be adding 1 more to the previous sum. So if it is necessary that we evaluate this and we get 0, but this is not sufficient enough for us to show that this converges. So we do have to show this first. We have to show that we're going to 0 here. Okay? So let's consider this next one. Let's consider our harmonic series. Okay? And you'll know in this one that, remember, this is our nth term does go to 0. We just proved that on the previous one. Okay? Remember, we had, that was this guy right back here. There he is, our harmonic series, the 1/2, 1/3, 1/4, and so on, that we keep adding to it. Okay? That guy right there. Okay? And so if you want to think of this, we have our first term is 1, and then we have 1/2, and then we add 1/4, or not, sorry about that, not 1/4, but 1/3, then 1/4, then 1/5. We keep adding those together. This was 1, 1/2, 1/3, 1/4, 1/5, 1/6, and so on. Now, crazy thing about this one is that when we look at this function here, as you recall, this is going to be the sum from n equals 1 to infinity of 1 over n. And this one is going to end up diverging, even though this does go to 0. This will give us no sum whatsoever. And we know that because, remember, this function here, 1 over n, by our p-test, that diverges. Okay? And that's just going to be the sum of all of that total area from 1 to infinity. So please understand, when we evaluate this one with our nth term test, if the nth term goes to 0, then we need to do something else. We can't say for sure whether this converges or not. If it does not go to 0, then we can be done with the problem, move on to our next one, because this will diverge. Okay? Let's take a look at our next one. And the next one occurs when we have a geometric series. Remember, with a geometric series, we always have a common ratio or common multiple. Previous one's twice as big or half as big. Okay? So, and this is the one, or these are one of the very few series where the sum is actually easy to find. In a geometric series, as you remember from our review of algebra, we have the explicit formula that takes that first term and then multiplies it by the common multiple or ratio to the n-1 power. In other words, when we take the sum of this, we're going to go from n equals 1 to infinity of that first term and then the common ratio to the n-1 power. Now, I will be rewriting these in different ways sometimes because your AP exam will sometimes rewrite them in different form, and they're really the same thing. So you can see I can also go from 0 to infinity on this one, but of course then I don't subtract 1. This would be just to r to the nth power. Both of these are the exact same series. They have the exact same terms in it. Okay? So the terms and ratios can be integers or variables. So this ratio here, r, it can be an integer. It can even be a variable, like x squared. The ratio is used to determine if the series converges. The geometric series will always converge to the first term divided by 1 minus that common ratio if the absolute value of that common ratio is less than 1. If the absolute value of that ratio is greater than or equal to 1, then the series will always diverge. So if we look at this one up above, you'll see in this one that our first term, this guy right here, was 3/10. The common ratio, each time we're multiplying by 1/10 times 1/10 times 1/10. Okay? So that's our common ratio of 1/10. Now, let's evaluate this. The absolute value of that common ratio is less than 1, so we know for sure that that will converge. Okay? So even though the nth term test said this might converge, now using the geometric series, we know that it definitely converges. Okay? And as a matter of fact, we can even find that value. This series from n to infinity of, I'm going to rewrite this so you can see it in that form that we have here, okay, or close to that. You'll see that this sum is going to be our first term, 3/10, divided by 1 minus our common ratio. So you're going to have to practice up on your fractions again on this one. This one could be a no calculator since it is relatively easy to find. So you'll see that that would be 3/10 divided by 9/10 multiplied by your reciprocal. That'll end up giving you 3/9 or 1/3. This sum is going to be 1/3. Okay? And hopefully you can see that it really is 3/10 plus 3/100 plus 3/1000 plus, and hopefully you can see that, doesn't that sure look like an infinite number of 3's, which of course equals 1/3. So this is 1/3, and that's the series that would represent the fraction 1/3. Let's take a look at a few more. In these, we're asked to find the first 4 terms of the series, and then rewrite it the general form, and then find the sum, and then determine whether it diverges. If it does diverge, then explain why. So you'll see this one will be 1/2 plus 1/4 plus 1/8. Those are our first 4 terms, so 1/16 dot dot dot. Then you'll see when we rewrite this in a general form and the summation, we should be able to say that the common ratio between each one of these is 1/2. The first term is also 1/2, and if we evaluate that common ratio, 1/2, the absolute value of that is less than 1. So therefore, this is geometric. So in here, I guess I should have put that up there. But our general form would be 1/2 times 1/2 to the n minus 1, which is just another way of writing the same thing, but at least writing it this way, it matches the previous form that we used. Let's go ahead and find this sum. Since this is geometric, and since our common ratio's absolute value is less than 1, we know that this must converge. And we can just use our formula, and that was our first term divided by 1 minus our first term. And of course, this proves what we just did on our square. 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32 is going to be 1/2 divided by 1/2, or a sum of 1. Let's take a look at our next one. First term would be 2 plus 2/3 plus 2/9 plus 2/27 plus, and let's write our general term. You can see that our first term is 2. Our common ratio, can you see where this is just each one being multiplied by 1/3 each time? And if we evaluate that, the absolute value of 1/3 is less than 1. So since this is geometric and we have this, we know that this will converge. And our general term would be first term 2 times the 1/3 to the n minus 1. And sometimes it will be written like this: t sub n equals 2 times 1/3 to the n minus 1. It's saying the same thing. So let's go ahead and evaluate this sum from n equals 0 to infinity to, that's going to be our first term, which is 2, divided by 1 minus r. This, of course, will be 2/3. So this is 2 divided by 2/3, which ends up giving us 3, multiplied by the reciprocal. Let's take a look at our next one. In our next one, you'll see that the first term, when k equals 0, we'll have 1 in the denominator. This will be 2. And then 2 will be in our numerator. When we do 1, this will be a -3, so I'll make sure that I change this to a negative. And then the next term will be plus 2 in the numerator. And then we are squaring this, so that'll be a +9. Next one will be 2 in the numerator, but now -3 is cubed, which will be a -27. Our common ratio between each one of these is actually -1/3. Our first term, t sub 1, is 2. If we evaluate the absolute value of our common ratio, this is still less than 1. Since we are geometric and we have that case, this will converge. Our general form of each one of the terms would be that first term 2 times -1/3 to the n minus 1. And we can find the sum of this by using that formula for a geometric series where r, the absolute value of r, is less than 1. And that is, again, the first term divided by 1 minus our common ratio, which in this case is going to be 2 divided by 4/3, 1 plus 1/3, multiplied by the reciprocal, and we're going to get 3/2. Let's take a look at our next one. This time they just give us this series, so you can see that maybe I can rewrite this as 1, write it as 6, 6. Okay. So each time you can see that I'm multiplying each one of these by 3 halves. That's the common ratio. 2 times 3 halves. This is 1 times 3 halves. 3 halves times 3 halves is 9 halves. Our first term, t, is 2/3. If we evaluate our common ratio of 3 halves, you'll see that it's greater than or equal to 1. Therefore, there is no sum here. This series diverges. Let's consider this next geometric series. This is a geometric series, but because you can see that each term is the previous term times x. So our common ratio here is x. Our first term is 1. Now, this will converge. We have what's called an interval of convergence if the absolute value of our common ratio is less than 1. In other words, this will only converge when the absolute value of x is less than 1. Or we can say that our domain, which again is kind of the same thing as our interval of convergence, will have to be from -1 to a +1. Domain and interval of convergence are interchangeable. So if they ask you for interval of convergence, or they ask you for what is the domain where this series will converge, then you're evaluating where r is less than 1. In this case, since r equals x, it's just the absolute value of x is less than 1. Okay. Now it says, let's write the function that gives us this series. Well, we know that f of x then is going to have to be our first term, 1, divided by 1 minus r. And this will only apply for all values of x between -1 and 1, or the absolute value of x is less than 1. Let's take a look at our next one. In this one, you'll see each time our common ratio is multiplying by a negative. We go positive, negative, positive, negative. And 4 times, in this case, 2, and then times 2, then times 2. And then it's also times x times x times x. So our common ratio is -2x. Our first term is 4x. Let's get our interval of convergence. Our interval of convergence will be when the ratio's absolute value is less than 1. In other words, when the absolute value of -2x is less than 1, or the absolute value of x is less than 1/2. Therefore, our interval of convergence is from -1/2 to a +1/2. That's our domain, or interval of convergence. Next, it says let's write the function that will give us this sum. This function will be the first term, 4x, divided by 1 minus our common ratio. That will work for all values of the absolute value of x that are less than 1/2. Or more common, they do write it like this to show that x is between those two, but I don't care which one you use. So that concludes our notes for 13.1. Hopefully this is something that goes well for you guys, since it is a review of series and sequence that you had in some of your previous algebra classes.